All right. All right, there we go. Okay, so we are in section 9.2. The section is called Trigonometric Integrals. And we are basically going to be looking at a whole bunch of problems that have powers of sine and cosine and tangent and secant, okay? For this section, we're going to leave out cosecant and secant, so we're really focusing on sine and cosine, secant and tangent, okay? So we're going to start off with this left-hand column here, what we know. And we have these two questions right here, okay? So this first question says the integral of cosine cubed sine x dx. And this is actually something that we are able to solve. And we're actually able to solve this using u substitution. Okay, so that's just something that I want to remind us about, that we can use u substitution in a lot of cases, and it's almost like a really good thing to check for before you start doing any of the other kind of like crazier, more complicated processes that we're learning, okay? So here's how I know that I can use u sub. I look at this and I say, okay, I see cosine, and I know that the derivative of cosine is negative sine, and I see a sine in there. So I see a function and part of its derivative in the same integrand. And so in this case, I'm going to go ahead and let my u be cosine x, okay? So with u substitution, it's generally a good idea for folks to have the u be whatever is raised to a power. So in this case, cosine is raised to the third power, so I'm going to have u as cosine. That's going to make my du equal to negative sine x dx, okay? And I know that I have a sine x, but not a negative sine x, so I'm going to divide that negative to the other side, and I'll get this, okay? Now, when I substitute all of this into my integrand, I'm going to end up with the integral of u cubed times negative du. And so that negative is really a -1, so I can bring that negative out in front of my integral. And I really end up with negative the integral of u cubed du, okay? Now, this is a really nice integral because all we need to use is the power rule, and it's a whole number power, and it's a positive power. And so all we're going to do, we're going to bring down that negative sign. We're going to say u to the 3 plus 1, which is 4, and then the coefficient will be the reciprocal of that power. And then because I don't have bounds, I want to make sure I have a plus c here, okay? But with our u substitution and a lot of the substitutions we're going to be doing over the next week, we want to make sure that if our question is asked with x's, we need to have our answer with x's as well. So that's going to make this negative 1/4 cosine to the 4th x plus c. Okay? So just another kind of situation where u substitution can be really helpful. Now, if we take a look at this second question down here under the what we know, thoughts on whether we can use u sub or not for this? What do you guys think? Yeah, okay. And what would we have as our u in this case?
Sine x?
Yeah, we'd have the sine x, right? So the sine is the one that's raised to the power. And so kind of like we had cosine to the 3rd as our u, now we want to have sine as our u, so we'll end up with u to the 4th, okay? So u equals sine x dx. And that means du equals cosine x dx. And that matches perfectly in the u sub. So now I can put everything in. I'll end up with the integral of u to the 4th du. And really straightforward here. All I need to do is use the power rule. And so u to the power of 4 plus 1 gives me 5. And then I need the reciprocal of that as the coefficient, 1 over 5, and then plus c. And as tempting as it is to put a box around that as the final answer, our initial question was asked with x's, so our final answer needs to be answered with x's. And so we'll end up with sine to the 5th x over 5 plus c. Okay?
Really quickly?
Yes.
When you set u, do you need to set it equal to sine x and dx, or is it just sine x?
I meant to set it to sine x. Thank you for that.
My bad.
All right. So with these two right here, and by the way, I really appreciate when folks correct me. I really do, genuinely, because especially in the internet age that we're in, these are going to be posted and someone else is going to watch them and be like, who is this person who doesn't know what she's doing? So thank you for saving me from that. All right, so I wrote the answers for these two questions a little bit differently, just because those are probably the two different styles that we see a lot. And some people like to write it like this, where the sine to the 5th x over 5 is like one fraction. And some people prefer having sort of the fraction in the front and then the cosine to the 4th next to it. Either version is fine. I'm not really picky about that, but I just wanted to show you both ways are definitely okay. All right. So if we kind of look in the column next to it, there's this whole column of what's new. All right. And for all these questions, these are going to be the examples that we go through today in class. And before we go through them, I want us to take a look at these and maybe focus in on one or two of them and talk about why we can't use u sub. Okay, I think that's the most challenging thing about this unit, is making that decision, like, can I use u sub or do I have to use this more complicated technique? So let's take a look at this first question right here, this sine to the 5th x dx. So take a moment, maybe kind of think about why we can't use u sub for this. And then if someone either wants to share out in the chat or just share by unmuting yourself, what do we think? Why can we not use u sub for that very first question?
Because we don't see a part of its derivative?
Yeah, we don't see a part of the derivative, right? I see the sine, which is awesome. It kind of looks like that second example I did, but there's no cosine to go with it, which means there's nothing to substitute that du with, okay? We can kind of use that same reasoning for the second one. There's no cosine or sine with it, okay? Which means that there's nothing to substitute out that du, all right? What about these two questions? What makes those unable for us to use u substitution?
Is it because the powers don't match? So even if you took the derivative, you would still have one left over?
Yeah, these powers right here. So like if we go back a moment and we look at our du was not raised to a power. So if I try to use u substitution over here for these two problems, I'm going to end up with du to some power, and that's not something that we're able to solve right now, okay? Let me just check the chat real quick to make sure I didn't miss anybody's feedback here. Yeah, both terms are different powers. There's no du. Okay, cool. Yeah, so, and the reasoning is going to be very similar for the next four with the tangent and the secant, especially those last two. There's no substitution for the du, and then those first two, it's like you're going to have du raised to some power, okay? Yes.
But can't you use you know how in the first one there's a sine to the 5th power, and you could separate sine, like one sine, and leave sine times sine to the 4th, and that sine to the fourth, change it to a
Yeah, no, that's exactly what we're going
one.
to do. That's exactly what we're going to do when we actually solve these questions, okay?
Oh,
That
that's it.
technique, yeah, so that technique is technically not called U substitution. We might use U substitution along the way, but we do tend to have to separate some things to make it a little bit nicer for ourselves. Kind of like yesterday when we had that x to the fifth, and we split it into x to the third and x squared, and then that was able to help us use U sub. That's what we're going to be doing today.
Okay.
Okay, thanks, Alex. All right. One last thing before we move on, and that is we're really good at knowing the derivatives of sine and cosine. That, to me, was clear that yesterday people knew that, and I was really happy to hear that. And so before we move on, I just want to make sure we know the derivative of tangent. Anybody remember the derivative of tangent?
Secant s.
Yeah, secant squared. So secant squared x is going to be our derivative of tangent. Okay, so that's going to be something that we'll use in sort of the second half of class when we go over the problems that deal with tangent and secant. Okay. All right. So we're going to get started with the first section, which is on derivatives of sine and cosine, or integrals with sine and cosine, but in the case where sine and cosine are raised to powers, okay? So I included this little list of sort of like decision-making things. It might be really helpful to have this copied down on a cheat sheet that you can use for that exam number 1, okay? So I know we didn't talk a lot about exams yet, but the quizzes, to clarify, are open notes and open resources. You can work together on them. That collaboration is totally fine. The exams, however, are not collaborative, but you can have a cheat sheet. Okay, you can have a sheet where you write down formulas, examples from class, whatever you think is helpful. And so I've included a lot of these sort of like decision-making steps in here to kind of give you a guidance of like what might be important to write down, okay? So for example, if we look at these problem-solving strategies, integrating products and powers of sine x and cosine x, we're looking at things that have a form of something like this, okay? Now the J's and K's just represent potential powers for cosine and sine, okay? And this textbook has sort of broken it down into 3 sort of cases. So the first case is if you end up with an odd power for sine, then we're going to use exactly what Alex mentioned earlier, which is we're going to try and split it into 2 different sine expressions and use some substitutions and then ultimately get it to a point where we can use U substitution. Okay. Now, the same thing can be true when we're looking at a situation where the power of cosine is odd. So when powers of sine and cosine are odd, that's actually really helpful for us, okay? The trickier case is going to be in the situation where the powers are both even, okay? So like, for example, cosine to the 4th, sine to the 4th. That would be a case where both powers are even, okay? I also do want us to note here that even includes, not that, if the power is 0, okay? So sometimes we're like, well, what happens when it's not there at all? Like if there's no sine or no cosine, that means that that power is 0 for that particular term, okay? So even though I put these rules kind of up at the top, I think it's really useful to go through the problems and then kind of see how they actually get used, okay? So let's go ahead and take a look at example number 1. So example number 1 has the integral of sine to the 5th x, okay? Now, what that shows us is that this power, okay, which if we went back up, the power of sine is k, all right? So k, and in this case, k is 5, which means that k is odd. That means now we can use this strategy number 1, okay? So what are we gonna do? We're gonna take sine to the 5th, and we're gonna split it into sine to the 4th times sine x. So I'm gonna rewrite this, and I'm gonna say here, k is odd, okay? And so when I split this, I'm going to end up with the integral of sine to the 4th x times sine x dx, okay? Now from there, we're going to look to break down the powers of sine into powers of 2. So what I mean by that is sine to the 4th can be written as sine squared x squared times sine x dx. Now the reason why we want to break it down into powers of 2 is because then we can use one of the most common Pythagorean identities for trig, which is that sine squared x is the equivalent of 1 minus cosine squared x squared. Okay, so this sine squared x became 1 minus cosine squared x. And now what I have to do here is I'm going to take this power of 2, and I am not going to just distribute it like 1 squared minus cosine to the 4th squared. Don't do that. But what we're going to do now is we're actually going to FOIL this out, okay? So if I wanted to write it out sort of the long way for the first time that we're doing this, I would write it like this. And if you're the kind of person who always forgets to FOIL, this might not be a bad step to say, I'm going to commit to writing this every time so that I know that I'm not going to forget to FOIL. And what we're going to do is we're going to FOIL out this part, but we're going to leave this part at the end. So don't multiply in that end piece. And when we FOIL that out, we'll get 1 minus 2 cosine squared x plus cosine to the 4th x times sine x dx. Okay. Now our whole purpose for doing this, trig substitution, is so that we can get this to a point where now we can use u substitution, okay? So here's what we're gonna do. Every cosine x, we're gonna replace with u. We're gonna let u equal cosine x. So u equals cosine x, and du will equal negative sine x dx. And when I look at the problem, there's only a sine x, so I'm going to divide that minus 1 to the other side. And now we're going to substitute everything in, okay? So if I substitute in, I'll get the integral of 1 minus 2u squared plus u to the 4th times a negative du, okay? And that negative, again, I like to put that sort of out in the front whenever I can, so that I'm not including more negative signs and sort of confusing myself along the way. Same thing with constants, I like to bring those out to the front right away. And so what I've done is turned a situation where I couldn't solve it using U sub right off the bat, and now I'm using U sub like a few steps later on, okay? And so from here, I just really need my power rule. So the integral of 1 is going to give me U minus 2 times, let's see, U to the 2 plus 1 is 3, and then the reciprocal of that is 1/3, plus U to the 5th, because 4 plus 1 is 5, and 1/5, and plus C. Now, what we're going to do here is two things at the same time. We're going to distribute that minus sign, okay? So the minus is going to go to every single term here. And I'm going to put back in my U. So everywhere I see a U, I'm going to replace it with cosine x. So I'm going to get negative cosine x plus 2/3 cosine cubed x minus 1/5 cosine to the 5th x plus c. All right, so let's get that all on one screen so you can see that. But that is how we use those rules to help us kind of split it up into a situation where now we can use U sub, okay? All right, so let's take a look at example number 2, okay? So this is a situation where I look at the powers and I see that this power right here is 4. And that means that j equals 4. And that means that j is even, okay? Now, if I think about what k is, like what is the power of sine, there's not even a sign in the integral, so the power of sine is 0, and that is also even, okay? So this is like the very last step that we showed in those 3 steps there, which is a situation where we can't just say, let's make it into a U sub situation. All right, so let's go back and read what that number 3 says. It says if both j and k are even, we're going to use sine squared equals 1/2 minus 1/2 cosine 2x, and cosine squared equals 1/2 plus 1/2 cosine 2x. All right, so we're using here our, not our double angle identities, but our power reducing identity. Okay, so this is like one of the more obscure identities that you learn in pre-calc, and you're like, wow, when am I ever going to see it again? And the answer is right now. We're going to see it again right now. Okay, so these two substitutions, this cosine squared and sine squared substitutions are really useful in the situations where j and k are both even. Okay. So let's scroll back down to example number 2. And take a look at this. Now, if I think back to the rules, they gave me substitutions for cosine squared and sine squared, but not for cosine to the 4th. So we're gonna have to do the same thing we did in the other problem, where we take cosine to the 4th and we write it as cosine squared squared. And now we can make our substitution. So everywhere we see a cosine squared, we're going to write 1/2 plus 1/2 cosine 2x squared. Okay. So cosine squared became 1/2 plus 1/2 cosine 2x. Now, before I begin, okay, I'm going to say that let's go ahead and factor out the fraction. So I think it's important we know how to work with fractions, but I don't like working with fractions more than I need to, and I think this is a really clear case of that. So I actually write this as 1 plus cosine 2x over 2 squared. Okay, so I took the two fractions, I kind of put them back into one fraction. The reason why I did that is because now I can take this square, distribute it to the 1/2. So 1/2 squared gives me 1/4, and I can bring that constant right out to the front. So this will give me 1/4 the integral of 1 plus cosine 2x squared. All right, we're going to be doing a whole lot of complicated math, and so I think it's really in our best interest to kind of make it as uncomplicated as possible as we're going along. Now, again, if you are a person who forgets to FOIL things out, then I would recommend that you write it like this as a reminder to FOIL, okay? And if you're not a person who struggles with that, then you don't need to worry about that. But either way, we'll end up with 1/4 the integral of 1 plus 2 cosine 2x plus cosine squared 2x dx. Now, as I'm going through problems, I kind of like to do a check and see like, all right, am I there yet? Is there anything else I need to do? And really that comes back to the question of, can I integrate what I see? So I look at this and I say, for 1, I can integrate 1. Integral of 1 is going to be x. That is totally fine. This 2 cosine 2x, I can integrate that. But I'm going to need u sub, okay? The problem, though, comes here, the cosine squared. I'm not any better off because I had cosine to the 4th and I couldn't do that. Cosine squared by itself, I still can't do that. So what we're going to need to do is make another substitution, okay? And so what I'm going to substitute in is I'm going to use that double or the power reducing identity. So I still have my 1 plus 2 cosine 2x plus, but instead of cosine squared 2x, okay, so we had cosine squared x equals 1 plus cosine 2x over 2. So if I want cosine squared 2x, that's going to give me 1 plus cosine 4x over 2. And the reason why it becomes a 4 is because whatever this coefficient is, it gets doubled here, okay, as part of that power reducing part. So this was an x and it became a 2x. And now a 2x becomes a 4x, okay? So when I substitute in, I'm going to put 1 plus cosine 4x over 2 instead of cosine squared 2x. All right, now what I'm going to do is I'm actually going to split this fraction into two separate fractions. All right, so I'll get 1 plus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x dx. And I'm going to see about combining some like terms. So for example, there's a 1 and a 1/2, and I can combine those to make a 3/2. So the integral of 3/2 plus 2 cosine 2x plus 1/2 cosine 4x dx. All right. One of the things that you'll notice that I do, I think I do them in the answer keys for the quizzes, and I'm going to try and do in the notes as well, is kind of label like what kind of integral rules I'm using. Because we're using so many rules in any given problem that it does get really confusing and overwhelming. So when I look at this I can solve using u sub. Okay. Where my u is going to be 4x. This one, I can also solve using u sub, and my u will equal 2x. This one, I just need power rule. Okay. So let's go ahead and set up our integrals. So I've got 1/4. Then I'm going to multiply to everything here. The integral of 3/2 is 3/2 x plus the integral of cosine 2x is going to be 1/2 sine 2x plus 1/2, and the integral of cosine 4x is going to be 1/4 sine 4x, and I'm going to need a plus c at the end. And then we're going to go ahead and combine all of our fractions. We're going to distribute that 1/4. So let's see. The first term becomes 3/8x plus 1/4 sine 2x plus 1/4 times 1/2 times 1/4 is 1/32 sine 4x plus c. Okay. So there's the whole problem on one screen, all right? You can tell that these problems are long because in the notes I left like a whole page for every problem. And that's kind of a reality of our first unit. Some of these questions are going to be really, really long. And I think if you're a person who likes to skip a lot of steps, it can be really hard to go back and find your mistakes. As you can tell, I make mistakes as well. So the more that I write out, the easier it is for me to figure out how my mistake impacts all the other things, okay? So how we doing here? Folks have any questions? Okay. All right, so let's move on to example number 3. Okay. And what I'm going to have you do is take about a minute or so, look back at those 3 rules at the beginning and see which rule you think you're going to use, okay? And then after about a minute, I'll go ahead and put my setup up here, and then we can kind of compare and make sure we're all understanding how to make the decision, okay? Not just how to do the math, but more importantly, how to make the decision.
Real quick question.
Yeah.
Is our goal to get both of those powers to an even?
No, not necessarily. So if I go back up to the rules, we want to think about how we can, like, which one of these is going to get us started, okay? So for example, this question has an odd power for cosine. So this one is going to take precedence even though the k power is even. Does that answer your question?
Yeah.
Okay. All right. So we've got this cosine cubed, and really the questions are much easier if one of the powers is even. Okay, so example 1 was a lot shorter than example 2 because that power was odd, and this one will be shorter than example 2 because one of the powers is odd. Okay, so if you see an odd power, you should be like, yes, odd power, because it's going to make your life easier. Okay. Now, I did want to write down that Pythagorean identity. So sine squared x plus cosine squared x equals 1. That's kind of how we all learned it. But variations that we tend to use a lot in these kinds of problems, we either solve for sine squared, in which case we get 1 minus cosine squared, or we solve for cosine squared and we get 1 minus sine squared. All right, so if in the previous problem you were like, I don't know where she got that Pythagorean identity from, that's not actually the identity, it's just an algebraic simplification of that identity, okay? So if we come back to this problem, when we see an odd power, we're gonna split it into one less than that power, which makes it even, and then a singleton. So in this case, this is gonna give us the integral of cosine squared x times cosine x times sine to the 4th x dx. Okay. Now, what I'm going to do in this next step is I'm going to do a substitution. So I'm going to take 1 minus sine squared x, and I'm going to replace the cosine squared x with the 1 minus sine squared x, okay? The other thing I'm going to do is I'm going to take this cosine x and I'm going to move it to the end. And so when I do that, I will get 1 minus sine squared x sine to the 4th x cosine x dx. Okay. Now, I thought someone asked that really great question earlier, do you have to kind of worry about both of the powers? And the answer is no, because in this case, look what happens. I'm going to take these two sort of terms, and I'm going to take the sine to the 4th, and I'm going to distribute it to the 1, and I'm going to distribute it to the sine squared. That's going to give me sine to the 4th x minus sine to what power here?
6.
Yeah, it's going to be 6, all right? So that 2 and that 4, because I'm multiplying the signs, I'm going to add the powers. So 2 plus 4 gives me 6. And then I've got my cosine x dx hanging out at the end. And that is so perfect because what I've set myself up for now is u substitution. So everywhere I see the sine x, I can replace that with u. Okay, so u equals sine, u equals sine x, du equals cosine x dx. That means that all of this at the end gets replaced with du. So I don't even need to worry about it. In fact, it was so perfect that I was able to keep one of those cosines to help me create a u substitution situation. And so now when we substitute things in, we'll end up with u to the 4th minus u to the 6th du. And that's a problem that I know you guys know how to solve, right? We're just going to use power rule. So we're going to get u to the 5th over 5 minus u to the 7th over 7 plus c. But because our question started with x's, we need our answer with x's. And so that will give us sine to the 5th x over 5 minus sine to the 7th x over 7 plus c. And that is our final answer. Okay, so there's the whole problem on one page. Again, when one of those powers is odd, it's going to make our lives a lot better. Okay. All right, so let's go ahead and take a look at example number 4. And I'm going to give you a few minutes this time to kind of get started to see if you can set up this, figure out what substitutions to make. And in about 2 or 3 minutes, I'll start putting my work up there. Okay. So I'll go ahead and scroll down to example number 4, give you guys a couple minutes to get started, identifying which steps we want to use. Okay, so hopefully when you looked at example number 4, you were like, yay, the power of sine is 3 and 3 is odd. So that makes our life a little bit easier, okay? And so when we see that odd power, we're gonna split it into 1 minus that power to make it an even power, and then a single sine or single cosine, depending on which one you're working with. So I split it and I got sine squared x, sine x, cosine to the 4th x dx. And so now I'm going to substitute that Pythagorean identity. So instead of sine squared, I'm going to have 1 minus cosine squared x. And at the same time, I'm going to bump that cosine to the 4x in and move the sine x to the end. And again, we're setting ourselves up for that u substitution, okay? Now I'm going to go ahead and distribute that cosine to the 4th to the 1 as well as to the squared. And that will leave me with cosine to the 4th x minus cosine to the add the powers 6x times sine x dx. And this is all set for our u substitution. Cosine is going to be our u this time, which means that we're going to end up with u equals cosine x, du equals negative sine x dx, and we're going to have to move that minus sign to the other side. When we make our substitution, we'll end up with negative the integral of u to the 4th minus u to the 6th du. So this looks really similar to our other problem. The biggest difference here, there's a minus sign right here, and there is a different u. Okay, so when we end, we're going to have cosines in our answer, not sines in our answer. So this will give us negative u to the 5th over 5 minus u to the 7th over 7 plus c. And we're going to make sure we put all of our proper variables back in. We'll end up with negative cosine to the 5th x over 5 plus cosine to the 7th over 7 plus c. All right, So folks, that brings us to the end of the first half of 9.2, where we've looked at powers of sine and cosine. So how are we doing so far? Are there any questions that are coming up for folks?
I have one small one.
For sure.
It might be obvious, but you know that plus c on the very end?
Yes, sir.
That plus c will not be attached to the integral, so it doesn't need to have the negative be distributed to it. It will always just be a plus c, correct?
Yeah, so the thing about c is c could be any number. So we could distribute it and make it a minus c, or we could say plus a negative c.
Okay, would we still get credit for it if we?
I think more traditionally, everyone just leaves it as a plus c, and they're like, well, we'll worry about the value of c when we actually need to solve for it. So for example, if you go all the way up to differential equations, you're going to solve for c a lot, and then it'll be important to have, once you have the number, it's important to have the right sign. But when it doesn't have an actual number and you don't want to solve for that number, then you kind of don't really need to worry about it.
Okay, thank you.
Okay. All right, any other questions coming up for folks right now? All right. Yesterday, I know we took a 5-minute break. Was that helpful for people? Would we like to continue to do that when we can? Or would we rather just kind of plow through? Okay. Okay. All right, awesome. I mean, it helps me too. I was like, I can't talk for that long. I start to lose my voice. All right, so let's go ahead and take a break. Let's reconvene at 10:26. Okay, so we'll be back here in about 5 minutes. All righty. So let's take a look at integrals with products and powers of tangent x and secant x, okay? So a lot of these strategies are going to be very similar to what we looked at before, in the sense that we're looking to, if things are even or odd, is going to help us make some decisions. Okay, now there's an extra rule here, and it's not as cut and dry as the sine and cosine ones, but I think once we do a few of those, we'll start to feel a little bit more comfortable making those decisions. Okay, so again, the k and the j just represent, like the k in this case is talking about powers of tangent, and the j is talking about powers of secant. It doesn't really matter what letters you use as long as you know that you're looking at the power of tangent versus the power of secant, okay? And so we have a few rules here that if the power of secant is even, then we're actually going to split it so that we end up with a secant squared somewhere along the way, okay? And this secant squared is there because we said earlier the derivative of tangent is secant squared, okay? That's why we need to pull 2 of the secants out, because that is going to help us with the u-sub situation, okay? Now, there's this another case where maybe the power of tangent is odd. And in that case, we're actually going to lose a power from each of them. We're going to lose a power from tangent, and we're going to lose a power from secant, okay? Now, what that gives us is a secant tangent at the end. And so earlier, I had us write down that the derivative of tangent x is secant squared x, okay? But I'd also like us to write down that the derivative of secant is one of those that we're like, I never really see those in a problem, so I don't need to know those. But the derivative of secant is secant tangent. Okay, so that's why in that second rule, we're looking to produce a secant tangent at the end, because both of those are going to help us with the u substitution. Okay, so the only reason it looks maybe more complicated than the sine and cosine is because the derivatives for tangent and secant are not as straightforward as the derivatives for sine and cosine. Okay, so there is a case where k is odd and k is actually greater than 3 and j equals 0. Okay, so this is more of a specialized case. But at the end, what we're trying to do is also look for a way to get it into a form where you can use u substitution, okay? And then there's this last case, if k is even and j is odd, then we're looking to separate it so we have tangent squared equals secant squared minus 1. And then all that stuff that we learned yesterday, integration by parts, comes in as sort of the second step of that problem. Okay, so the second steps that we've seen so far, it's mostly like rearrange these things and then use u substitution. But sometimes you're going to rearrange these things and then use integration by parts. Okay. I know it sounds delightful, doesn't it? Okay, so what we're going to do here is we're going to write down one of the Pythagorean identities before we go on. And I'm sorry I didn't leave room for that, but we'll kind of squeeze it in right here. Okay, so the Pythagorean identity we talked about earlier was sine squared plus cosine squared equals 1. But there are two other Pythagorean identities that are really useful, and especially when we're talking about the tangent and secant, there's one that involves tangent and secant. Okay, so tangent squared x plus 1 is going to equal secant squared x. Okay, that means that I might use a version where everywhere I see that tangent squared, I use I use secant squared minus 1. Okay, so that's where this substitution comes from. It's a different form of a Pythagorean identity. Okay. I know this chapter is like a lot of different rules and identities that you're like, I don't know, someone told me a while ago, but I never had to use them, so I forgot them. And we're definitely going to be using those now. All right, so let's take a look at this example number 5. So I'm going to look at the powers and kind of think about what might be important. So my power of tangent in this case is 3, okay? So k equals 3, which is odd. Now, which one of those 4 rules or strategies might be helpful in this particular situation?
2.
Yeah, that second one, right? Because k is odd. How come it's not going to be the third one?
Because tangent's not by itself.
Yeah, because tangent's not by itself, right? There is a secant in there. So that means we got to use strategy number 2, okay? And so strategy number 2 says that we're gonna, if k is odd, we're gonna lose the power from the tangent and we're gonna lose the power from the secant. And that's gonna give us the secant tangent that we need for a u sub at the end. So that would give us the integral of tangent squared x secant to the 4th x, because I got to lose 1 from each of them. And at the end, I'll have 1 tangent x and 1 secant x. Okay. So what does it say after that? After we've rewritten it by losing a power from each one, we're going to use the substitution, tangent squared equals secant squared minus 1. So again, that's from that Pythagorean identity. So this is going to give me the integral of secant squared x minus 1 times secant to the 4th x tangent x secant x dx. So from here, what we can do is we can go ahead and distribute, okay? So we're going to take that secant to the 4th, and we're going to distribute it here, and we're going to distribute it here. Okay, so we're going to keep these together, and we're going to keep those at the end and not worry about them yet. This is going to give me secant to the 6th x minus secant to the 4th x. And then I've got a secant x tangent x at the end. Okay. Now the reason why I kind of switched the order of the tangent secant at the end is because it's the same thing, right? Like I could say 2 times 3 or 3 times 2, it's the same thing. But secant tangent helps remind me that I've got the derivative to help me take care of my du. And so now we're ready to do some u sub. So everywhere we see a secant, we can go ahead and replace that with a u. So u equals secant x. That means that du is secant x tangent x dx. So we're able to get rid of that whole piece with just a du. And that will give us the integral of u to the 6th minus u to the 4th du. Go ahead and use that power rule, u to the 7th over 7 minus u to the 5th over 5 plus c. And don't forget to have your final answer in terms of x's, not u's. Secant to the 7th x over 7 minus secant to the 5th x over 5 plus c. Okay. And so there we've got the first problem of the secant tangent variety. Okay. Any questions on example number 5? Okay. So let's go ahead and move on to example number 6. All right. So with example number 6, I'm looking again at the powers, right? And so I look and I'm like, well, this power for tangent is even. So I can't use the same rules that I did for example number 5, okay? But there is a rule where this power for secant is even. And lucky for us, in this case, secant power is even. So our j is 4, which is even, okay? And so before we start, let's go back up to that rule and see if we can remember what the steps are, all right? So we'll go back up. And so when j is even, that's gonna mean we use rule number 1. And what that means is we're gonna split the secant square, or secant to the 4th, into powers of 2, all right? So I've got secant to the 4th, so I'm going to split that into secant squared and secant squared. So that's going to give me the integral of tangent squared x, so that one stays. But instead of secant to the 4th, I'll have secant squared x times secant squared x dx. And now what I'm going to do is I'm going to take one of these secant squareds, and I'm going to substitute in tangent squared plus 1. Now, the reason I'm not going to do both of them is because, remember, we're trying to create a situation where we have a du that we can substitute, right? And the derivative of tangent is secant squared. So we're kind of saving this one for the u sub, right? And so now we can distribute tangent to the 4th plus tangent squared, and then secant squared x dx at the end. Now we can use our u sub for tangent. So u equals tan, and du equals secant squared x dx. So that takes care of that whole piece at the end. And so we'll get the integral of u to the 4th plus u squared du, which looks way easier than our initial problem. And now all we need to use is power rule. So u to the 5th over 5 plus u cubed over 3 plus c. And then our final answer is not going to have u's, it's going to have tangents in it. So tangent to the 5th x over 5 plus tangent cubed x over 3 plus c. Okay. So if we pause for a moment and think about how this compares to our sine and cosine situations. Sine and cosine is kind of nice when the powers are odd. Okay, and that was kind of a general rule that we can make. If the powers are odd, our problem is going to be easier. When our powers are even, then we have to deal with that power reducing identity. Okay, but with the secant and tangent, we have to shift that narrative a little bit, and we have to think about if tangent is odd, that's a good thing for us. And if secant is even, that's a good thing for us. Okay, so as you're looking through these rules and kind of practicing that decision making, be really explicit with yourself, especially as you go through those quiz questions, like how am I making these decisions, not just, well, this looks most like this question, so I'm going to do it this way. Okay, practice that decision making, and I think that'll help you feel more prepared for next week's exam. All right. So we've got 2 more examples here, all right? And we're gonna take a look at example number 7 right now, okay? Now, example number 7 is gonna be really helpful for one of the quiz questions, because at some point in the quiz, you need an integral for tangent cubed. So it's okay if you just use the answers from here to help you get that integral in the quiz, because you'll be doing plenty of other work before you get to that stage, okay? So let's take a look at the powers. The power here is 3. That means that k equals 3 and it's odd. So that's very similar to the first example we saw, right? Example number 5. However, and someone pointed this out really well earlier, in this case, there's no secant. So J is 0. So let's scroll back up and take a look at, I always worry that I'm going to make someone motion sick when I'm scrolling too fast. But so let's take a look at these steps and read number 3. So if k is odd and k is greater than or equal to 3 and j equals 0, then what we're going to do is we're going to split the tangent. So we've got a tangent and then a tangent squared, okay? That's going to allow us to substitute the tangent squared with our Pythagorean identity. That's secant squared minus 1. And then we're going to be able to distribute, okay? So when we go back down to example number 7, we're going to split the tangent cubed into tangent and tangent squared. And everywhere we see the tangent squared, we're going to replace it with secant squared minus 1. And then we're going to distribute. Okay. Now, I'm actually going to do this first part here, okay? So when I look at the first term, this one, I want to go back to the first question that we talked about yesterday, which is, do I see a function and at least part of its derivative in the integrand? And the answer here is yes, because I see a tangent and the derivative of tangent is secant squared. So my strategy for this first part is going to be u sub. And my u will be tangent x. My du will be secant squared x dx. Okay. The integral for tangent, okay, however, is actually a good one to know. So we're going to add that to the list of like good integrals to know. You don't need to derive it. You just need to have it written down on your cheat sheet. Would probably be a good idea, okay? But this one we can pull from our table of integral. So if you think back to maybe when you were like in middle school or high school, if you actually had like a math textbook, and in the cover of the textbooks, there's always like all these different formulas. So there's sort of, when you look at calculus books, usually either in the covers or sort of at the end in the appendix, they have a table of integrals. And that table of integrals is a list of all the common integrals. And so tangent x is on there, as well as secant x. And so we're going to see that in the next question. Okay. So when I set up my u sub for the first part, I'll end up with the integral of u du minus, and then this tangent x, if I look up the integral for that, has two different answers, okay? One of those forms is the natural log of secant x. I'll show you the other form in just a little bit, okay? But our integral of u is just going to be u squared over 2. So I'm using the power rule, and I'm going to go ahead and put my tangent right in there. So tangent squared x over 2 minus natural log of the secant x plus c. All right. So this is one version of your answer. Now, if you look in the table of integrals, there's another alternate way of saying the integral of tangent x. So I want to show you that one as well. This part will stay the same, but the integral of tangent could also be negative natural log of cosine. So if you wanted to write it this way, I would probably at least take that extra step to do a plus natural log of cosine x plus c. And that version would also be okay. All right. So either one of these is fine.
Could you tell me how you got tangent squared x over 2 for the u du?
Yeah, for sure. So the u sub here is, if I take the integral of u du, I'm going to end up with u squared over 2. And what was my u? My u was tangent, so that's where I get the tangent squared over 2.
Oh, I got it. Never mind. Thank you so much.
Okay, perfect. All right. Any other questions on number 7 so far?
Yeah, when you did that u sub, did you just do it for half of what was in the integral? And
Yeah.
then you just,
So with integrals, if you see things that are connected by addition and subtraction, you can essentially treat it as individual problems.
all right, yeah, so you could just rewrite that as two integrals. Okay.
Yes, for sure. Good. Any other questions so far? Oh, I see one in the chat. Rule number 1. We used rule number 3 here, Omar, because there's no secant, so that's like the special case. Okay. I hope you guys don't mind me using your names. I feel like sometimes it's like weird talking to my computer, and I would really like to know your names. So, okay, so let's do our last problem here. All right, so our last problem is example number 8, and we have secant cubed x dx. And so what we have here is our power of secant is 3. Or we could say j equals 3, which is odd, okay? And so let's go back up to our rules and see which strategy is going to help us out with that one. And so when I look, I see that my secant is cubed. So the power of secant is odd. And the only rule that has the power of secant being odd is the 4th one. And you might say like, well, but there's no tangent, so it's not even. But remember, if there's no tangent, that means that the power of tangent is 0, which is even, okay? So what are we gonna do here? It says we're gonna use tangent squared equals secant squared minus 1 to help us express different parts of that, okay? So let's go ahead and scroll back down. Okay, so we're gonna take our secant and we're gonna split it, kind of like we did our tangent in example number 7. So we're gonna split this to be secant x times secant squared x dx, okay? And the reason why we're splitting it like this is because now we're gonna be able to use integration by parts, okay? Now there's no tangent here for us to substitute because this is a special case where the power of tangent is 0. That's why we're not using the secant squared minus 1 part, okay? But the idea of integration by parts here is still valid. So if I split it like this, I have 2 things to choose from as my u. I could choose secant x as my u, or I could choose secant squared x as my u. Which one of those is easier to take a derivative of?
Secant squared x
You secant.
or
It's
just
just,
secant?
yeah, the secant is easier to take the derivative, okay? But the other question is which one is easier to take the integral of? And that would be the secant squared, okay? So that's kind of how I pick and choose when they're on the same level. Like they're both trig, so how do you know which one's your u and your dv? Like the lipet and the liate falls apart when they're both the same. So the other question you want to ask yourself is which one is easier to take the derivative, which one is easier to take the integral? And that's kind of how you choose when they're even playing levels for both of those. So our u is going to be secant, and our dv is going to be secant squared. All right, so u equals secant, du equals secant tangent. dv equals secant squared x, which is so nice because the integral of secant squared is tangent, okay? And so now we're going to put these into our integration by parts. And this is going to give us u times v minus the integral of v du. So I'm going to take the secant and I'm going to keep that. And then the tangent and this tangent, I'm going to multiply and make tangent squared. Okay. So here's the beauty in what we've done. We still have to do a little bit more work. But what we did is create a situation, not red, we created a situation where we got that tangent squared. And the tangent squared we can replace with secant squared minus 1. And so we're going to get secant tangent minus the integral of secant x times secant squared minus 1 dx. And I'm going to go ahead and distribute here. Now, I will take the time to go ahead and split this into 2 different integrals here. So these 2 right here, I could split it into the integral of secant cubed and the integral of secant. Okay. And that second one became a plus because this minus sign I have to distribute here, and I have to distribute to that minus sign there. Okay. All right, now let's see what we have. Our original problem was the integral of secant cubed. So secant cubed, and look what we ended up with. On the other side, we ended up with another secant cubed. And so this is like those circular problems we encountered yesterday where we had to move all the like terms to one side and then divide by that coefficient to get our answer, okay? So if I write the whole thing out, I get the integral of secant cubed x equals secant x tangent x minus this integral plus that integral. And so I'm going to take this secant cubed and I'm going to add it to the other side, which will give me 2 secant cubed dx equals secant x tangent x plus. Now, earlier I said, you know, the integral of secant is a good one to know, or integral of tangent is a good one to know. Integral of secant is also a good one to know. So this integral right here, okay, the integral of secant is going to give us the natural log of secant x plus tangent x. And again, I just got that from a table, either the back of a book or, you know, online. So that would be a good one to know as well, because we'll see the integral of secant pretty frequently as we go. And then we need our plus c. And then our last step here is just to divide by that 2. So I get the integral of secant cubed x dx equals 1/2 secant x tangent x plus natural log of secant x plus tangent x plus, whoa, plus c. Okay. All right. So here is the question on the full screen. Any questions on this last example here? All right. Well, if there are no questions on the lecture, then I'm going to stop the video right now. If you don't have any questions on the quiz, you're welcome to take off. If you do have questions on the quiz and you'd like to hang around and ask me those questions, you're more than welcome to do that. Okay?
I have one question on the quiz.
For sure. Let me just stop this recording.